So let's look at some sample problems. What are the other products? Which type of decay is this? And how much energy will be produced? Looking at the top numbers, we're going from 232 down to 228. That's a difference of 4. The bottom number is going from 92 down to 90. That's a difference of 2. So this tells me that the other product is a hydrogen atom, and that tells me that it's alpha decay. To figure out how much energy is produced, we're going to add up the particles on the right side and compare it to the mass on the left side. That difference is called a mass defect, and that much mass has turned into energy during this decay. Our shortcut for calculating the energy is to multiply by 931. So we have 5.4 mega electron volts. The other way to calculate this is to convert it into kilograms. Use Einstein's equation, E equals mc squared, and that gives us our answer in joules, and then we can convert joules into electron volts. We'll get 5.4 times 10 to the 6 electron volts. Second problem, what are the other products? Which type of decay is this, and how much energy is released? Looking at the top number, 14 stays the same. Looking at the bottom number, 6 is turning to 7. That tells me a neutron is turning into a proton, and that is beta decay. So the other particles are electron and antineutrino. The carbon has 6 electrons because it's 6 protons, and that means nitrogen also has 6 electrons. So it is missing one of the electrons, so it has a positive charge to it. Remember, the charges always need to be conserved. In calculating the mass defect, the antineutrino has no mass, and we don't count the electron that comes off because it came from the nucleus. It has no binding energy. And again, our shortcut, if we're multiplying by 931, it gives us 0.156 mega electron volts. Fission is breaking apart a large atom into smaller atoms through collisions. This is what we're doing inside of a nuclear power plant. They all do a fission process to create our energy. In the nuclear power plant, we are using uranium-235 and we're hitting it with a neutron. This creates an excited state called an isomer. This nucleus is actually vibrating and kind of wobbling. Now this nucleus is so large, it's kind of unstable to begin with, and this little extra energy from the neutron is the little kick that it needs to help break apart. The nucleus becomes more unstable because the protons are trying to repel each other, and the strong force is having trouble holding it all together because the nucleus is so large. The electric force then overpowers the strong force and the atom busts apart. It turns into 2 new atoms and we get 3 neutrons that are given off. Those new neutrons can go and hit other atoms and make a new collision and a new reaction and give off new neutrons that hit other atoms and so forth. This is called a chain reaction, and this is what we're doing inside the nuclear power plant. We're continuing a chain reaction over and over and over again to give off a constant amount of energy that we can harness in the form of heat. So down at the bottom, this is the equation for our nuclear fission. On the left side, notice the neutron has a 0 in the bottom because there's 0 protons, and a 1 in the top because it's 1 nucleon. And just like the other equations we've done, we have a conservation of particles. On the bottom, the numbers have to add up to 92. On the top, the numbers have to add up to 236. Now these products have less mass than the original atom did, and that means we're losing mass. That lost mass turns into energy. Fusion is the opposite of fission. It's combining smaller atoms into a larger one. This is what's going on in the sun and in other stars. They're combining atoms together. I'm going to go through the steps of the hydrogen fusion that the sun is going through. We start off with a special form of the atoms called plasma. The center of the sun where the fusion is taking place is so hot and so much pressure that the atoms all lose their electrons, and it's just the nuclei there. So we're going to start off, we have 2 hydrogen atoms that are going to combine into a new hydrogen atom, and that hydrogen atom has 2 nucleons, 1 proton and 1 neutron. This is called heavy hydrogen or deuterium. It also creates a positron and a neutrino in this reaction. A positron will meet up with an electron and they both annihilate each other, and both of those masses will turn into energy. We'll get two photons. In these kind of reactions, when we create a photon, there always has to be two photons created because they have to be going in opposite directions for conservation of momentum reasons. Our next step is we're taking the heavy hydrogen atom, the deuterium, and combining it with a new hydrogen, which makes a light helium. The helium has two protons and one neutron instead of two neutrons, and also another photon is given off. If we go through this whole process a second time, we'll end up with two helium atoms, and those two helium atoms can combine in the last step to make a normal helium atom, and we get two hydrogen atoms back out of it. And we get two hydrogen atoms back out again. So we've used a total of 6 hydrogen atoms to create one helium atom and 2 more hydrogen atoms. So our net result is 4 hydrogens have been turned into 1 helium. We've gotten lots of energy from this because mass is lost in each one of the steps, and we've got several photons given off. Next topic is the half-life. Half-life is the amount of time for half of the amount of atoms in a sample to decay into a different atom through one of these processes that we've been learning about. Example, cobalt has a half-life of 30 years. So if this square represents our cobalt, after 30 years, half of it will decay into a new atom and the rest will still be cobalt. After another 30 years, half of that remaining will turn into another atom. After another 30 years, half of that remaining will turn into a new atom, and so forth. So the kind of problems that will be given on this is asking how much will be left after 120 years if you started with a certain amount, 32 grams. So we went through 4 half-lives. We cut it in half once, again, and again. So we cut it in half 4 times. So each time we multiply those and we'll end up with 1/16 of the original sample. So this is a general formula we can use to figure that out. The amount left equals the original amount, and we're multiplying halves over and over again, or how many half-life cycles did it go through is the exponent. And to find how many half-life cycles, we're doing the total time divided by the half-life time. So the problem they gave us, 120 years divided by 30 years is 4. So we did 1/2 to the 4th power is 1/16, and 1/16 of the 32 grams then is 2 grams will be left. End of notes.